it is time to get right into our video conference today, and time to meet the man of the next 90 minutes himself. He's an expert astrophysicist. He's currently working at the Australian National University. He's doing various projects, including the extension of the work on his theory of the expanding, accelerating universe. Awesome and scary stuff. Please join me, ladies and gents, students across Australia, in giving a really big warm welcome to our VIP, Professor Brian Schmidt. Now, can I call you Brian?
Please.
Brilliant, great. Now, Brian, it's a pleasure having you in Questacon. You've just received a very, very prestigious award, the 2011 Nobel Prize in Physics. Congratulations.
Thank you very much.
Yeah, and has the buzz worn off?
Yeah, a little bit, I guess. The initial euphoria is now going into, I think, a sort of a new state where I sort of get it all the time, I guess.
Okay.
A little bit of excitement. But
Yep.
it's not just crazy like it was for the first day.
Wow, I can imagine. Now, you're no stranger to awards. You've got a whole list of accolades to your name. But this particular award, it's quite a big one. Were you nervous when accepting the award?
Yeah, when they called me up on the phone, I have to admit my knees kind of went a little weak, and it was a little scary, probably as scary as any other time in my life.
I can imagine. Now, just tell me, your family, they must be really proud of you. And you've got children. How many times, Brian, have you been to their school for show and tell?
Ooh, more than 10.
Yeah, more than 10, yeah.
But I'm not sure. I haven't been counting on it, I guess.
Okay. Now, the actual Nobel Prize itself, have you received that yet?
No, that happens in December. On the 10th of December, we go out to a big ceremony in Stockholm.
Okay.
And that will be where I get the piece of gold.
Oh, brilliant. Very excited about that, I see.
Yeah, should be good fun.
Yes. Now, let's stick to the theme of the science today and look back in time. You grew up in America, in the Montana mountains, and about age 13 you moved to Anchorage, Alaska. Now, science was in the blood. Your dad was a fisheries biologist. How was it growing up under his influence?
Well, I just loved science my entire childhood. We used to go out while he was working on his PhD thesis, and I would stick a net out the car, and we'd drive through the ditch, and I'd pick up all the bugs and stuff, which he had to turn into his class.
Oh, right.
So here he'd probably pick up snakes and other things, but in Montana, no snakes.
So no snakes. That's good. That's handy then. Now, actually, at age 5, Brian, you wanted to be a meteorologist. What changed?
I don't know. I went out and worked a bit for the National Weather Service, and for whatever reason, I thought it was interesting, but it wasn't quite the science I wanted to do, so I had to, think of something else to do, and astronomy was it.
Brilliant. Now, you did a Bachelor of Science too, in fact, of astronomy and physics. And then, ladies and gents, students across Australia, this is a record class, I feel. You did your Bachelor of Science, as the two of them, your Master's and your PhD in 7 years, University of Arizona and then Harvard. That's brilliant.
Yeah. Everything went well for me.
Yeah.
Sometimes things don't work well.
Yeah, I think so. Did you have a really big college life, or were you right to the books?
No. I've always had a balanced life. So to me, it's always a matter of balancing fun and working hard. So I try to do both well.
Now, did you have some professors or supervisors that really fostered that passion for astronomy?
Yeah, throughout my entire time, even at primary school and then in secondary school and at university, I've always had someone I could look up to and talk through, and that continues to this day.
Yeah, that's great. That's great. You met your wife as well, and she was Australian. She was studying at Harvard, and you moved to Australia. How was that?
Well, it was great. I had visited Australia twice when I was a kid for a couple months, and so I knew the place really well, and Canberra, for me, is a place that's not dissimilar to the mountains of Montana. I mean, I realize the weather's a little different, and you talk a little different, and I still talk different, but the actual way people work and do stuff together, very, very similar to the western part of the United States.
Okay, nice skies over in the southern hemisphere?
Yes, the Milky Way goes straight overhead here, so it's a great place to do astronomy.
I think we can only go into maybe a big presentation about what you actually do, Brian. I know I'm really excited to hear about astronomy and cosmology. So Brian, please take it away.
My pleasure. So, my challenge to you is to provide everything I know about the cosmos in 25 minutes, or maybe a little less. So, I want to start off, I think, with a quick tour of the universe, and so I'm hoping we'll cue my video up. There we go. So, we've already got from Monty Python in a song that came out when I was about 10, and I remember it well, our quick tour of the universe. And so what we're going to do is use as our ruler the speed of light. And the speed of light we use because it's something where we can convert distance into time. And you all have a good understanding of time ranging from 1/100th of a second to, for example, billions of years. And so it's a useful unit for us to use. So we're going to start off and remind ourselves that light travels around the Earth 7.5 times a second. It travels at 300,000 kilometers per second. So that's fast, but on the scale of the universe, it's not actually that fast. And so let's look at our universe and quickly go through. We start off with the Earth-Moon system, 1.5 light seconds. When Neil Armstrong got on and said his famous misquote, that quote went through Australia, but it took 1.5 seconds to get here because it's how far away the moon is. We go to the sun. Our sun is much, much bigger than the Earth-Moon system. It's 5 light seconds across. It looks the same as the moon, but it's much, much further away. It's actually a total of 8 light minutes in distance. If we go to our solar system, now our solar system is still 10 light hours, and although we've demoted Pluto, something that I voted against, Pluto still extends sort of as a marker towards the end of our outer solar system of planets. That's 10 light hours. It takes 10 hours for light to get out to Pluto. But that is really just a small drop in the ocean of what the cosmos are. So if we look at the cosmos on the largest scales, we can go through and look at the nearest star, Alpha Centauri. Alpha Centauri you will see as being one of the brightest pointer star to the Southern Cross, and that's the nearest star to our own. Alpha Centauri is a twin of the Milky Way, of our sun. And so if our sun were a pea, then the sun, the Alpha Centauri, would be another pea, located 200 kilometers away, with everything else in between empty space. And that's pretty remarkable when you think we live in a galaxy, the Milky Way, one of the most exciting places in the universe. But we're 30,000 light years out from the center, just as Monty Python told us. And so really the universe is a very big place with lots of empty space. If you look at the Milky Way from the top, it looks like a spiral, and that's why we call them spiral galaxies. And we're located out on the edge of a spiral arm. Now if we look out further to the nighttime sky, as I do almost every night before I go to bed, I like to have a look at the stars and ponder the universe. And when I do that, I look out and I see the nearest galaxies. The nearest galaxies are about 2 million light years in distance. They include the Andromeda Galaxy. The Andromeda Galaxy is not easily seen here in Australia, but much more close are the Magellanic Clouds, which are little fuzzy blobs towards the southern sky, which really won't look very impressive, but there are hundreds of millions of stars like the sun in each of those galaxies, which look like little clouds in the southern sky. Going on further, if we look and we make a map of the sky like we did here in Australia, about 2001 is when it was finished. This was the biggest map of the universe at the time. We measured 220,000 galaxies using a telescope, the Anglo-Australian telescope, up at Coonabarabran. And the universe, you can see, has kind of a foamy structure. It looks like a tangled web, and that's what gravity imprints onto the Milky Way, or onto the universe. So the universe is kind of a complicated place, and there we're looking out to 1 billion years. So we're going way before the dinosaurs at this point, back in time. But we can look further. The Hubble Space Telescope allows us to look back as far as we can see right now. And so here's a picture of the most distant reaches of the universe that we can see to this day, a place about 12 billion light years in distance. So we're looking back billions upon billions of years before the Earth was formed. Finally, we can keep looking back, but now we cannot look with optical telescopes. We have to look with microwaves. And the image that we take, if we take an image of the sky with a space telescope that is sensitive to microwaves, just like you might cook your lunch with, well, we're looking back to when the universe was very, very hot, when it was about 4,000 degrees in temperature, and the whole thing was glowing like a giant neon sign. And so we're able to look back to to this time right after what we think is the Big Bang, 13.7 billion years ago. All right, so that's a quick way to get ourselves all oriented on where the universe is structured. Let's see how we can figure out what the universe is going to do over time. So I think the beginnings of cosmology can be traced back to this man who none of you will have heard of, Vesto Melvin Slipher. One of the great heroes of cosmology who was overshadowed simply because he didn't have a good publicist. So Vesto Melvin Slipher I have particular fondness of because his family gave me a scholarship when I went off to university. And I have to admit, I didn't know who he was either when I got the scholarship, but I've soon found out because he is one of the greats. What he did is he took the light of galaxies. And when you take the light of galaxy and you spread it out into the colors of the rainbow, you get what we call a spectrum. And a spectrum has little inputs where you can see the fingerprints of atoms. Every atom has a fingerprint where it absorbs or emits light. And so when you look at a galaxy, it looks just a lot like our sun. Except for when Slipher did this, he realized that the spectrum was stretched redward a bit. And we believe that that's caused by the Doppler shift. So most of you will have known of the Doppler shift where you have, for example, an ambulance goes by you and the pitch changes so that it's higher when it comes towards you and it's lower when it goes away. When light changes pitch, it changes color. Light's coming toward you, its light becomes slightly bluer. When it goes away from you, slightly redder. And so what Slipher found out in 1916 is he was able to measure what the galaxy's motions were. And he found that all of the galaxies in the universe that he measured, minus just a few, were all moving away from us. And that was a conundrum in 1916. It would seem that we were a special place in the universe, seemingly a very unpopular place where everything was trying to go away from. So that was a problem we needed to understand because we didn't think we should be in a special place in the universe. We think we should be just like everywhere else. And we figured this out by measuring distances. Now, measuring distances in astronomy is really hard because we can't just lay down a ruler. We can't just measure the distance to the nearest star. We have to be clever about it. And the way we do it is by looking at things like what we call a standard candle. If you have a light bulb or a candle whose brightness you think you know, the further away that object is, the fainter it appears. And so by judging how bright an object is, if we know how bright it is, we can measure distances. Edwin Hubble did that in 1929. And he used the largest telescope in the world at the time, the Hooker 100-inch telescope, which if you ever go to Los Angeles, you can see up on the side of the mountain, just outside of Pasadena. And this new technology allowed him to make measurements no one else could. So astronomy back in the old days and today still is still driven by technology. Now, he didn't have a big standard light bulb. He was desperate. So he just made the assertion that when you see one star, one really bright star, you see them all. They're all the same brightness. And so by seeing how bright stars were, he could judge the relative distances to galaxies. And what he found was the larger the redshift, or the faster the galaxy was moving away from us, the fainter the stars were. That meant the further away the object was. And so in 1929, and Hubble had a very good publicist, he announced that that meant that the universe was expanding. Now, you may not understand why that means the universe is expanding. So first, let's look at his data, because I'm going to show you some of my data later on, and I want you to see what Hubble's data looked like. You can see here in this diagram, if we move from left to right, that the distance gets bigger this way, and the Doppler shift gets bigger this way. And so the further an object was in distance, the faster it was moving away. Now, if we look at a little toy universe, which through the magics of a computer, I can expand, and I overlay that expansion, you can see in this diagram that objects that are really near to where my reference point have moved a little bit. Objects that are a long ways away have moved a lot. If the universe is expanding, the further an object is away, the faster it will be moving away from us. We'll be doing a little demonstration of this later on with a balloon that you all have and a ruler. The other nice thing about this is you can overlay the data anywhere you want, and everyone sees the same thing. We're not a special place. If the universe is expanding, everyone sees the same thing. Now, if we have a universe which is expanding, then inevitably in the past, it was a smaller place. And that naturally leads you to a time when everything in the universe was on top of everything else. That's the Big Bang. So imagine, let's do a little thought experiment here. And imagine I have two galaxies separated by some distance now. In the past, they were closer, and I can draw a line of how fast the universe is expanding now, and I can extrapolate it back in time. At some point, those two galaxies are on top of each other. That's the time of the Big Bang. So how fast the universe is expanding tells us the age of the universe. Now, one of the things that was done at Mount Stromlo was to use the Hubble Space Telescope to accurately measure the age of the universe in this way. And the answer they got was 14 billion years. So how fast the universe is expanding tells us how old the universe is, but gravity pulls on the universe as it expands, so it'll slow it down over time. Just like if I throw a ball up in the air, I have to worry about gravity. The same thing happens with our universe and gravity. So my experiment isn't going to quite be the same. The universe is not necessarily just traveling at the same speed. It may be slowing down over time. And if it's slowing down over time, its trajectory is going to look like this, and the universe isn't actually going to be as old as we think. Now, we can always take that and move it forward. We can look forward. So imagine a universe which isn't slowing down. Well, that's a universe that's just going to keep on expanding in the future. So if we look at this trajectory, the universe just gets bigger and bigger over time. Goes on forever. It's infinite. But imagine a universe that has lots of gravity, so it's slowing down. This is a universe which will expand and slow down, reach a maximum size, and then start collapsing. And so where we get the Big Bang in the future of this universe, we get the Gnab-Gib, which is the Big Bang backwards. So measuring the universe's past is an interesting thing, and it was what I decided to do when I moved to Australia in 1994. It was something I felt I could explain to almost anyone. And so I wanted to measure how much the universe was slowing down over time. So my experiment was to do the following. I was going to recreate what Hubble did in the nearby universe, and I was going to see if, by looking by very distant objects, whose light takes billions of years to reach us, whether or not I could see whether or not the universe was slowing down over time. So imagine a universe which is slowing down over time, or not slowing down over time. It has nothing in it, no gravity, doesn't weigh much. Well, that's a universe whose expansion doesn't change over time. It'll be expanding the same rate in the past as it does now. Imagine a universe which has just the right amount of stuff, so that eventually, infinitely far in the future, it stops and starts to collapse. Well, it has a trajectory where long ago it was expanding faster than now, and it's slowed down over time. On one side of that trajectory, gravity wins, the universe ends, the universe is finite. The other side of that line, gravity loses. The universe keeps on expanding forever and is infinite. Big question. So, when we did our experiment, which I started, as I said, when I came here, 3 years later, we got the following answer. So here's the experiment, and I looked at this and I said, this isn't quite what I expected. If I draw my trajectory, you can see that that line, the points on the left side of the diagram, have an error. So there's an uncertainty for every point. So that's represented by the bar, essentially, up and down. And on average, you can't really tell what's going on. That's why we looked into the past of the universe. And there you can see that those points are not consistent with a universe that is going to collapse in the future. I was very disappointed. Aesthetically, I liked the idea of a universe which would eventually collapse. It seemed to be nice to have a beginning and an end. And I don't like infinity any better than anyone else. But my surprise was if I looked at where the universe should be then slowing down a little bit, because I know there is some gravity in the universe. After all, we are here. My points all were above the line, above that yellow area, in a place which didn't make any sense, where the universe was speeding up rather than slowing down. Now, when the universe is speeding up, that means we have a problem, because gravity pulls, right? Well, it turns out, according to Einstein, who's got the great theory of gravity, forget Newton, Einstein's the man, he came up with something called dark energy back in 1917. She later said, it was a mistake. It is also known as the cosmological constant, and it was proposed by Einstein back in 1917 because his equations of general relativity said the universe should be expanding. But of course, we didn't know the universe was expanding back then, and so consequently, he had to come up with a fudge factor. And this fudge factor is energy tied to space. So it says, what's empty space? If empty space is empty, nothing happens. And we see this, every experiment we do now, we see evidence for this stuff. But it's funny stuff. We can only see it on the grand scale of the cosmos. The other thing you will have heard about is stuff called dark matter. This is stuff that has normal gravity just like atoms, but we can't see it either. So we're in the rather embarrassing situation as astronomers of having 95.5% of the universe unaccounted for. We can see its effect in gravity, but we can't touch it. 4.5% of the universe are the atoms that we see. That is the frosting on this cake of the universe. Now, some people would say, that's crazy. I said, that's crazy. It means we don't know what's going on, right? So the way science works is we then test this theory. We do new experiments. And those experiments over the last 10 years have consistently shown that this experiment, this set of parameters, describes the universe we live in. And until we show that that's wrong, it is really the only explanation we have for the universe we live in. So what's the eventual outcome of this? Well, we call it the big chill. Dark energy is part of space itself. As the universe expands, more dark energy gets made. And so the pushing increases. The pulling, which our atoms and dark matter is doing, which does not get created as space gets created, stays the same. So over time, the more space expands, the more dark energy that's made, the more pushing occurs, which causes more space expanding, and the universe expands faster and faster and faster over time. Eventually, as the universe expands so quickly, we end up in this situation where even light from galaxies that we see today will no longer be able to reach us. Because space is expanding, as they travel through space, that light gets stretched more and more and more and eventually gets caught up in the expansion because the expansion rate happens faster than light can travel itself. And we will live in a cool, empty, dark universe which just fades out into time. All right, so one of the things that we do is we have to measure distances. And so I talked about the idea of standard candles. Well, we need a giant light bulb, and what we use are things called supernovae, exploding stars. And so one of the things that I studied is how exploding stars explode. They're very important because they make all of the iron and stuff that makes up life here on Earth are created in these supernovae. And so their physics is very interesting. They are the largest bangs in the universe since the big one. So they are important in all ways. So let's talk just briefly about how a supernova might happen. Our sun, in about 5 billion years, is going to grow quite big, and the Earth is going to become toast. And at the end of that, we're going to end up with a little star called a white dwarf star, which is the mass of the sun, all in the size of the Earth. Now imagine our sun were a binary star. That first star, the larger of the two, will become a white dwarf star, just like our sun will. And then the other star will eventually do the same thing a little later and will start spilling material onto the first white dwarf star. Chandrasekhar, who won a Nobel Prize long before me for being very, very smart, realized that those things go boom when they reach 1.38 times the mass of our sun. And these big explosions are what we're going to do a demonstration. We want to understand how these explosions occur. And the big problem that we have in understanding supernovae is whether or not they explode slower than the speed of sound, which we call a deflagration. And when they do that, instead of making things like iron, they make what we would call soot, nuclear soot, like oxygen and silicon. And so Patrick, who happens to share the same hometown as me, we talked to the mayor and he said, no, put Patrick, he'll be the sacrificial lamb. And I'm going to get out of camera. And so this is a deflagration. I want you to concentrate at the balloon. Now, if a supernova does that, it makes carbon, it makes oxygen. It's really good for life, but it doesn't make much iron, doesn't make much gold, doesn't make anything else interesting. And so the question then comes, if they detonate, then you make almost entirely iron. Now, a detonation is something that happens faster than the speed of sound. So instead of getting something that goes woof and expands, speed of sound means that nothing can react to the speed of sound. And so the balloon will not expand at all, and it will burn much, much more quickly. And so we have a smaller balloon here for an obvious reason. We'll see. So this one's fresh. Now I want you to concentrate on this balloon and see how much it expands. Notice there's almost no soot this time. It was clean burning. It made iron if it were a thermonuclear bomb. This is some other unnamed gas bomb to protect the less than innocent. So in the lab, we actually explode these things for real in computer simulations. We use supercomputers like the one here located in the ANU campus. And here is a real simulation of what we think one of these supernovae go. What we think happens is they start off as the first sooty explosion. And then for physics that's not completely understood, but very similar to what makes your diesel engine cause the diesel to combust and actually make the car run, these things go from being slower than the speed of sound to faster than the speed of sound. And so by using physics, we can, which was developed actually partially in the automobile industry, we can go through and understand these distant explosions. And so when Patrick comes back, we're going to go through and hopefully get one that does what it's supposed to. We'll see. Good to see science is always, well, you never know how it's going to turn out.
All right, now we might, while Patrick's getting ready, we might actually ask if we have any questions. So Rob over here is probably being on the emails, but have we got any studio audience questions for Professor Schmidt here? We have a few, so we'll just get our mic runners. Amy, I see one right in the middle. We're just heading on up. You can raise your hand quite high for us, please. And Amy, can you see her? She's just, yeah, brilliant. Oh, the nervous questions.
All right, Amy.
Thanks, Amy.
It's all on. It's on.
I was wondering, in your opinion, do you believe that there's actually an edge to the universe, like currently, the way that they originally believed that there was an edge to the Earth?
So that's a very good question. So the answer is not really. There is an edge in time. So I believe that when we go back 13.7 billion years ago, not 13.9, not 13.5, we run out of time. And so the edge of the universe back in time is the only edge we have. Our measurements right now indicate that the universe goes on way beyond anything that we can see. It's at least 100 times bigger than the furthest distances we can see. And we think it is very close to being infinite, although it's always impossible to extrapolate on beyond where you can see with absolute certainty. Even if the universe were to to curve around, it turns out it would curve around just like the Earth if it were finite, in which case it would have no edge again. It would just be a universe which you would head out this direction, and given enough time, you'd end up where you started, just like you would do on Earth. So space is warped around in a fourth dimension, which is related to time, and makes it very difficult to visualize things in your head.
Now we do have a high-speed video of that. If we wanted to roll that, boys, we can show you exactly what was happening at that time, and you can also describe it if you like, Professor Schmidt.
Okay? So in this case, we're going to go through and explode, hopefully, two different balloons, one of which, well, let's have a look at it. So that is a deflagration, and that is more or less the detonation. And so this one, you can see it keeps expanding, it breaks a long time to burn, and it's slower, and so consequently it ends up, in this case, being made out of hydrogen, so the residue would be water and just hydrogen. And so it gives you really an idea of what you saw up really quickly up here.
Brilliant. That's a great explanation, and that was definitely a bang worth waiting for. So can we have more questions? I think Rob's going to take over. Our schools have questions.
So if we could cross to Hutchins. Matt, can you unmute your microphone and tell us if you've got a question for Brian? These things take a moment. They're all the way down.
He's got a question. He's got a
Long way.
question.
There we go.
There we go. Okay. Have you got a question?
So how did you actually prove that it was expanding?
So the universal expansion was not proved by me. That was proved by Edwin Hubble. And so he did it by measuring distance and measuring how velocity. And so just like the balloon that we're going to do, or my little demonstration, if you have a universe which is expanding, then the further points are away, the faster they will be moving apart. And so when we go through with our balloon, we're going to be able to explore this in detail, and hopefully you'll get a sense of how it will all work.
Thank you.
Nice.
Thank you guys down there at Hutchins. By the way, Hutchins are one of our more experienced video conference schools. We've been conferencing down to them at various occasions over the last 2 years, so thanks guys. Woo. St. Peter's Lutheran College in Brisbane, are you there?
You know when you said that the
Here we go.
the sun was expanding and gonna heat the Earth up, how would the sun expand and heat the Earth up?
All right, so the sun right now is 5 light seconds across. That's its size. And the reason it's as big as it is it has a big nuclear furnace in the side. And so although there's all this mass, the sun is many, many thousands of times bigger than the Earth. And so heat makes pressure. Pressure pushes out against gravity. And gravity, of course, pulls in against the heat. And so the sun is in balance. Now, in the future, the sun is going to quit burning hydrogen in its core, which is how that nuclear furnace works now, and it's going to start burning hydrogen on a shell of material a bit further out. And that makes the sun heat up and produce a lot more energy. And so to be in balance, it's going to produce a lot more pressure, and that means that it will expand out to a new equilibrium where gravity and pressure are in equilibrium. And that, unfortunately, is about where the Earth is. That's how much it's going to puff out. But it's 5 billion years in the future. We don't have to worry about it tonight.
Sweet,
Okay,
thank you.
Brilliant. Thanks, Cleveland. Thanks for joining us. We're going to cross in a moment to St. Peter's Lutheran College, but in the meantime, let's take another question from our audience here. Has anyone got a question for Brian? Okay. Can we get a microphone into the middle here?
Hi. You said that the universe is infinitely expanding. And the Great Cool. Would you say that the Great Cool would be irreversible? Because if it wasn't constantly expanding and gravity kicks in, pulling everything sort of back into the centre, you can imagine it sort of restarting the process. Would you say that that Great Cool was irreversible and the end of everything, really?
So that's an interesting question, and the honest answer is, because we don't really understand dark energy very well, it is possible that dark energy will change in the future. And if dark energy is able to change in the future into dark something, dark matter or something, then it is possible for it to reverse things. If it is Einstein's version, that is energy that is just tied to space, then that never changes. And yeah, the universe is pretty well lost at that point. So until we understand dark energy, we don't know the answer to that question. But it does give us some hope that maybe something can change in the future. But that would require this funny stuff to change in a way that's kind of hard to understand. So Einstein would say, we're gone. It's irreversible. It's just going to keep going.
Okay, we're going to cross to Peak Central School in a moment and then to Corrion College in Victoria. But meanwhile, we've got a question from Xavier Poole from St Mary MacKillop High School. Are you here, Xavier? Right up the back there, you've got a question for Brian.
Yeah. As an explosion, sends things flying away, couldn't the expansion of the universe be caused by exploding supernovas?
So for that question, which wasn't on the mic there, we had, as an explosion is happening with a supernova, you were saying that couldn't the expansion, because, so Brian, would you like to?
So the difficulty is the way the universe is expanding, it's actually space itself which is expanding. And so if I blow a supernova up inside the universe, it expands, but it doesn't drag space with it. So what we're seeing is actually space itself expand. And the only way we understand how to do that is through Einstein's equations of general relativity. And so science is not just about going out and seeing things, it's about explaining it. And the way we test things is by Einstein's equations, make very specific predictions about how Mercury goes around the sun, how light bends around the sun, and how the universe should be expanding. And so at this point, it's really the only way we have to understand how the universe is expanding and how space itself is expanding.
Okay. Xavier, you had another question about a bit of a popular culture bent. Do you want me to ask that as you haven't got the microphone? Okay. Brian, do you watch Star Trek?
Which version?
Which version? All of them.
I'm an original series, so the original series started the year I was born, so I only saw it in repeats. I kind of went off on the later ones, but I'm a big fan of the Big Bang Theory now. So.
And the movies are pretty good too.
Yes.
Yeah, okay.
Except for number 5.
Except for number 5, yeah, the death of Star Trek. Corrion College, I know you're there because I saw you earlier.
We're here.
You're there, cool. Has one of you got a question for Brian?
Sorry, who's this for us?
I was just wondering what the relation to black holes and all of the expanding universe theory was.
Very good. So black holes are found throughout our universe. We see them in the middle of our own galaxy. We see them form after supernovae, not the type I use to measure distance, but a different type of exploding star. We see them sometimes form there. So they are places where we can test Einstein's theory of general relativity very accurately. And so it is a place where it's sort of an experimental test bed for us to test the laws of physics. But for the expansion of the universe, since black holes make up such a small part of our universe, less than 1%, they don't actually affect things too much. So we do see them, they're interesting, but in terms of the expansion of the universe, they don't have that much effect.
Okay, fantastic. And we've got time for one more question. Let's try Melton College in Victoria. Melton's only just installed their video conferencing equipment, so it's all brand new. Melton, can you unmute your microphone? And let's see if you're there.
Hello.
Excellent.
Okay, just a question to the professor. We've been bombarded with lots of information about how us mere humans are causing so much trouble with climate change because of the carbon. Is this going to have any effect on the Big Bang Theory or the expanding universe? I mean, it seems to be having effect on anything else in the world. Could you explain that?
I'm afraid that we, mere humans, while we seem to be able to affect things here on Earth, because Earth isn't very big, the universe is huge. And so we're going to really struggle to affect, at least with current technology, the universe on its largest scales. But unfortunately, you know, when I fly off to the UK or something, I get to see half the world, and the world is just not very big. And so we as humans can affect the Earth in various ways, sometimes good, sometimes bad, and that's something we just have to deal with over the next 100 years. Because what we do will matter, I'm afraid.
Okay, thanks, Brian. Okay. Hopefully we'll get a chance to cross to some of the other schools shortly, but let's cross over to the interview stage now to hear some more personal information about Brian's science and career.
Thanks, Rob, and thanks everyone for all those questions. I think they were really great questions, and it's great having so much participation all across Australia and in our studio audience. Now, I want to talk to you about dark energy. I know you say you don't know much about it, but how does it feel to have 72% of the universe unexplained?
It's kind of embarrassing, actually.
Okay.
So, you know, in across physics, we describe this as somewhere between, we like to say in a positive way, it's the biggest mystery.
Yeah.
Or we also like to say it's the biggest embarrassment. And so to my mind, it's kind of an embarrassment that 72% of the universe was able to be discovered by me and a group I work with. So that's kind of an embarrassment in their own right, because it didn't seem like I should be able to uncover that. It would be quite a big surprise, for example, in the linen closet, if you just suddenly wandered into it. So I think not understanding so much of the universe, and remember there's dark matter as well, which other people have seen. So the fact that we only understand 4.5% of the universe is a big problem for us as physicists. It makes us think or suspect maybe we're missing something big.
Does this actually make you question the results of your work then? I mean, you went in with your team, the High Z Supernova team, and as well as your affectionately termed rivals at the Berkeley lab. Now, did you think that if you both came to this decision and conclusion that your results were contrary to your hypothesis, that are they actually valid or right at all if dark energy is acting on them?
So of course, the fundamental result that we did was that the universe is accelerating, and the idea of dark energy is our best guess, but it's not guaranteed to absolutely be the solution. We don't quite understand it yet. But when we, at the end of 1997, started getting this answer, and we didn't know what the other team was getting, we just knew our answer was crazy, I of course figured we just made a mistake. But at some point as scientists, you go out and you try things, and they don't go away, and you keep trying it, and at some point you have to believe in your experiment and put it out there, just like we're seeing right now with the faster-than-light neutrinos. Sure. You have to put it out there, see if other people can reproduce it.
Now, speaking of other people, is it hard to get your work reviewed? I understand in the wider scientific community, it's great to get more peer reviews and confirmation that you're on the right track. What's that process?
So typically in science, you have a process where you write a paper, and then it goes to a place which is published, and it is reviewed by other scientists to make sure that what you're doing makes sense, is consistent, and it follows certain practice. And if you don't like those people, you can go get another review, and we can see, you can sort of work with the journals, as we call them, to ensure that you get a fair hearing.
Sure.
Now, some people who have really controversial ideas struggle because often they're not consistent. It's not that they go against the current orthodoxy, they're just inconsistent what we already know. And so that's where people fall afoul of that process. But to my mind, it's a very important way to ensure that the most credible information is out for everyone to use. And once it's out there, of course, it doesn't mean it's absolutely right, but it means it's past a bar.
Okay, so in your instance then, Brian, I would say that it's quite remarkable that you have managed to have this breakthrough theory due to the fact that you've questioned the most fundamental understanding of physics in our universe so far, not only Einstein's cosmological constant, as it's termed, and also the general theory of relativity. So, you know, that's big stuff.
Yeah, it was a big thing. So, you know, I was scared to death when we published in 1998 because I thought, wow, this could be the end of my career if I'm really, really foolish and I've done something stupid. Because when you go out as a scientist and you make a complete idiot out of yourself, especially when you're young, it's not a good look. Now, it doesn't mean they're going to fire you and stuff, but it certainly would be a bit humiliating. But in the end, you just have to back what you've done, know you've done a careful, good job as best you can. And so, yeah, we put it out there, and the reaction was surprisingly positive.
Yeah, it obviously worked, and it's obviously being accepted. Now, you said the breakthrough was 1998. What sort of work have you been doing on the program so far?
So since 1998, we've gone from only a few supernovae to thousands. So we've been able to refine our measurements, you know, with a great deal of precision, and we keep on getting the same answer. But I think more importantly, we've encouraged other people to go out and do different experiments that looked at the same question.
Sure.
And that work, a lot of it's been done here in Australia, continually gets exactly the same answer we do. So everyone is getting the same answer. It's crazy. We keep testing it, and I'm continuing to test it now in Australia. But, you know, if it just keeps working, that's the way science works.
Exactly. You're right. Now, you do most of your work at Mount Stromlo at the moment. There were some fires in 2003 in the Canberra region, quite devastating. Was any of your work damaged or lost?
Yeah, so in 2003, I had just started a program to map the entirety of the southern sky with the Great Melbourne Telescope, it was known. We have a piece of the Great Melbourne Telescope back here, actually.
We do.
And so the experiment I was doing was going to find lots of nearby exploding stars so that we could go through and trace out what the universe was doing locally. And that, unfortunately, came to an abrupt end 18 days after my program started when we burned to the ground.
Oh, that's devastating.
Yeah, it wasn't good.
No, it would not have been a very good day. We have the piece here if you'd like to.
Yeah, so this is a little piece of the 50-inch mirror of that telescope, and there's lots of little pieces like this that we have hanging around. And it's kind of pretty, but kind of sad at the same time.
I can imagine. Now, we might leave this for a moment, and you said before there was some sort of demonstration we could do with a balloon to talk about supernovae and how they expand and how you measure it. So what we might do is we might get you to come up again with Patrick, and our schools as well. We sent you some balloons, I can see some on the tables there, and some flexible rulers. So you can participate this as well. And our studio audience, of course, you have your balloons and your flexible rulers. So we'll get you over on the stage with Patrick.
All right, Patrick, comrade. So, nothing profound here. What we're going to do is we're going to recreate measuring the measurement I did, at least for measuring the expansion rate now. We can't actually go back in time with the balloon. But imagine we have a balloon. What I'm going to have you do is you're going to measure essentially the Hubble constant, or how fast your balloon is expanding. And what we're going to do is we're going to mark a balloon, and I'm just going to mark a little balloon here so I know which one. And then we're going to measure the distance to a nearby star, and I'll choose this one, and a distant star, and I'll choose that one. Okay? So if I measure the distance to the first one, I get 1.5 centimeters. And if I measure the distance to the second one, I get 6 centimeters. Now I want you to blow that balloon up for us. All right, I'm feeling that's probably big enough. Now, I need to locate my stars. This is always the hard part. So, now I look at it, and I go the first one, and I realize now it's 2.5 centimeters. So that first star has moved 1 centimeter. And the other star, which was 6 centimeters, is now at 12 centimeters. So it's moved 6 centimeters. So if you're going to measure the Hubble constant, what you're going to do is you're going to pair 12 centimeters. The further an object is away, 12 centimeters, and it's moved 6 centimeters, so that would be its velocity over 10 seconds. And in the nearby universe, something that's only 2.5 centimeters has moved 1 centimeter. So if you were to go through and do this for a whole bunch of stars, you would find the further the objects were away, the faster the balloon had expanded, or the more they had moved as you blow it up. And if you draw a little graph, you plot things, you'll get a nice little line. That is the expansion rate of the universe, exactly as we do it when we use stars. In our case, we measure the distance to stars, and we see how much they're expanding. And it's analogous to exactly what we're doing in this two-dimensional universe that's spread into 3 dimensions. Our universe, of course, is this 3-dimensional universe spread into 4. Okay? So that's a good thing to try at home and see how well it works. Thank you.
Brilliant, thank you. Now, guys, you can also do this at home on your own, or you can do it back here now. You can do it in the studio audience. We heard our balloons going off there. I think we may have some questions. Rob, if you'd like to take some questions either from the studio audience or from our schools.
Yeah. Could this have any implications to science, this new theory?
Now, he was asking if it had any implications for science, your new theory.
So what do you mean by science?
Well, the fields like chemistry and physics, would it change any of the basic laws?
So that's a big question. So one of the problems we have in science today is we have gravity and we have quantum mechanics. Gravity and quantum mechanics, we don't have any way to combine those two things. And one of the predictions, the fundamental predictions of taking gravity and quantum mechanics together, is that dark energy should exist. But we're off, the predictions of that theory are off by a number which is one of the largest numbers in the universe. It's a number of 1 with 120 zeros behind it, or 10 to the 120. So we always describe it as the biggest problem, biggest mistake, the biggest prediction error in the history of physics. So that's our best solution right now.
Wow, it
and
sounds
so,
scary.
yeah, our hope is that maybe we can put those together and use the idea of the dark energy we see and resolve this problem about how gravity and quantum mechanics work together.
That's a big job.
It's a big job for someone smarter than me.
All right. Maybe the student that asked that could work on that,
In the future, yes?
Exactly.
Okay, I think we've got time for a question in the audience. Has anyone in the audience got a question? Oh, these Gungahlin students, they're right in there. We've got some students over here, though, from Carabar. Sorry, guys, just to spread the questions around a bit. Is that...
Not on.
This isn't on? Yes, it
Yeah.
is. Yes, it is. Okay. I want to use... I may be misquoting quite seriously here, but I think it was Bolter who said that there was... Who observed that he called this animal energy when he would, connect 2 different metals to a frog and it would move its leg.
Yep.
I'm sure you're familiar with this. Now, this was repeatable and he could observe this, but he, of course, came up with a completely inaccurate thing. What I mean to say, is this possibly applicable to this, where we have 95% of the universe, and it seems to only have an effect in this gravitation? Is it possible that we've just given it a name, and we've just given one thing a name?
So that's the $128,000 question, as we say. I don't know what we call it, a couple $1 million.
A couple of million, yeah, let's call it
thanks to inflation. So yes, so the way we test this is that dark energy makes predictions. So one of the things that we went and looked at, which I haven't shown you today, are sound waves, how ripples in the Big Bang were formed. And the idea of dark energy and dark matter make very precise predictions of what we should see in these map of what we call the cosmic microwave background, or when the universe was really young. And so the ripples that we see there, the sound waves, have exactly the characteristic shape that was predicted before they were observed. So we were able to take this theory and predict something with it. And that's the basis of all science. And so we will keep doing that. And so my job right now is not to show that my measurements in dark energy are right, but I'm trying to show that they're wrong. So I'm always trying to go and find a thing that breaks the theory. And so that's my goal. The acceleration is not going to go away, I think, at this point. I think that's pretty experimentally verified. Understanding it, that's the hard part. And so you're absolutely right. You sort of have a gut feeling that this 95% just seems too crazy to be true, but it keeps on predicting what we see, and that's the problem.
Now, we're heading to the end of our video conference, and I'd just like to ask you, Brian, you have a pretty bright future ahead of you. What's in store? Tell us about SkyMapper.
So when we burned down in 2003, one of the things that the university allowed me to do was to start a new project, which we call SkyMapper. So it's a new telescope, like the one that I was going to use, but supercharged.
Right.
So it has Australia's largest digital camera that's been built up our new center up on the mountain.
Sure.
268 million pixels.
Okay.
Each pixel's 100 times better than what you would have in your own digital camera. And that's going to be mapping out every square inch of the southern sky, looking at billions of objects and creating what I would describe as a treasure map of the sky, which we can use to shine or to point our biggest telescopes on to the most interesting objects in the universe. Objects like Pluto, but that haven't been discovered, new Plutos, try to get it reinstated as a planet by giving it friends, and the most distant objects in the universe, so we can see how the universe was literally created after the Big Bang and the first stars and galaxies were formed.
So you could find maybe the first 100 or so quasars or stars in the Milky Way.
Exactly.
Would you name them?
Oh, well, for the right donation, I'm sure we could come to...
Okay, great. I think we have a huge audience that will want their name.
Yeah, I'm sure this is a very well-off audience.
I think so. Now, that's astounding in itself. The Milky Way, the first 100 stars. So you'll develop this catalogue using SkyMapper. Would you do a sister project in the Northern Hemisphere?
So I would if I had infinite amounts of time and infinite amounts of money. So I'm sort of hoping my colleagues in the Northern Hemisphere will figure out how to complement this survey. But at this point, they're doing some things, but I think they're waiting to see how we do. This is a really hard project.
Sure.
We are taking petabytes of data. A petabyte of data is 1,000 terabytes. And a terabyte, I think most people understand, is 1,000 gigabytes.
Yeah.
So it's a lot of data we got to get through.
Heaps of data,
Yes.
but very small pictures.
Yes.
Now, SkyMapper is brilliant, but what about SKA, the Square Kilometre Array? This project, would you like to explain?
Sure. One of the big things that Australia has invested in over the last 50 years is a series of monumental astronomical programs. So we started with the Parkes radio telescope. We built the Anglo-Australia telescope. We have a telescope called the Compact Array, which is located near Narrabri. And now we're going into the next generation, which we call the Square Kilometre Array, which is a next generation radio telescope. And I think maybe I should just show you where it's at, because it is truly in the middle of nowhere. And if I go through and show you, hopefully this zoom in, we're going to go in, and I think we all know we're in Australia. We're going to zoom in to Western Australia, to a place called Murchison-shire. And out here is this desert plain, which is 160 people in a size, a huge area. So there's almost no radio interference. And the idea is to have a square kilometer, so that's a collecting area of a square kilometer of high-tech radio antennas, which will allow us to look back in radio waves into places where we've never really been able to do it. We really want to look back to the dawning of galaxies and stars when the universe was just created and watch the universe light up for the first time. And so this is a huge project where we're competing with South Africa for hosting the site. I think we have the best place. Another panel will figure that out over the next couple months, and I think in February or March we should know the answer to this.
In 2012, wow. That's very exciting, and it does correlate to your SkyMapper project anyway, so you will have quite a role in there. Now, talking future of science here, can you maybe give us some words of wisdom as to why you feel that science education in particular is one of the best ways that a student could also study, not just their universe, but the world around them as well in everyday life?
So in the future, more and more jobs are going to be, you're going to need to be skilled. You can't just assume life's good, I'm going to go out and I'm going to get a great job. Because the world is becoming more and more competitive, and the people that you're going to be competing with are not just the fellow students, they're going to be people from China and from Singapore, from the United States. And so an education is fundamental to that. And science and technology is what has driven prosperity since the end of the Dark Ages. It's just been continual. And so if you have skills and interest in science and technology, it's really almost guaranteed to bring you success. There's almost, I've never seen in all my years an unemployed astronomer. Now, it doesn't mean they work as an astronomer. Many of my students have worked in anything, but they know how to do things. They can figure out and solve problems, and it's a great career. I think almost everyone I know loves their job.
Sure, and it's not just a clinical lab coat and experiments in a laboratory. Is it? You yourself have had an illustrious career, traveling and...
Yeah, you get to meet really interesting people. You get to travel around the world and use $100 million or billion-dollar pieces of equipment. You get to use interesting, cool computers and write programs to make them do things. Get to give talks like this. I mean, they're all pretty fun.
Exactly. Now, is there anything trending in science right now? Any professions or careers that you feel are more prominent than others at the moment?
Well, I think here in Australia, astronomy is really amazingly successful. But I think there's lots of things in, for example, nanotechnology, where they're going to use tiny little particles and they can make them behave in funny ways through quantum mechanics to do things that are just not possible right now. And then there's the whole area of microbiology, where you go through and figure out how to rearrange cells in such a way that you can cure cancer or, make wheat that is 3 or 4 times more productive than we are now to help stop starvation, for example.
Brilliant. So things that can really be fruitful towards, the future of Australia and the world. I know here at Questacon, we obviously are huge advocates, like yourself, of science education, and it's something we really believe in. So all of our schools participating today, we understand you all have a keen interest in science and the furthering of that, as well as our studio audience. Now, I think we have just some final moments for a couple of questions. I'm just looking towards the studio audience here, and Rob, you'll be asking some students through the email, perhaps. So anyone in the audience have a question?
Yeah. Jasmine, if you want to move
Yeah, sure. We've got one here, if we could get the mic again.
Okay. How did you tell your kids when they were growing up what you did for work?
Well, one of my kids is here, just down the road from thing. So what did I do? We just talked about what I did, and I've never forced my kids to do science or anything. I want them to do what they want to do, and so for me, it's just something I talk about in my work. And if they ask questions, I'm happy to discuss it. But I really let them drive the conversation, and so I think my kids have a fairly normal science background, actually. I mean, they obviously can ask any question, and sometimes I can even answer it. But I'm very good at math, actually, it turns out.
Oh, really?
Yeah, I'm great at helping on math.
Would you like me to read it? Okay, I'll read it for you.
What inspired you to become a scientist, an astronomer?
So why did I become an astronomer? I don't really know. It was sort of an accident, because when I was 17, I had to go to university, and I said, I don't know what I want to do. Most of you won't know what you want to do. And so I figured I would just go off and do something which I enjoyed, which I didn't think would ever provide any meaningful employment in the future. But I knew it would train me. I knew it would make me think, and I know it would provide me skills that I would eventually be able to use to get a job. So I really went out there because I didn't know what else to do. And I always expected I would do something else, but it never happened.
Brian, you're an inspiration to every Australian aspiring to be a scientist. Who or what inspired you to achieve the ultimate prize in science?
So I never really thought about winning a Nobel Prize, quite frankly. I always thought that I would just do the best job I could. And so winning a Nobel Prize was not something I really thought too much about. I really wanted to, I was really interested in what I was doing, so I wanted to know the answer. That's what really drove me.
Okay.
And when you get an answer, if I had measured that the universe was going to slow down and end, well, I wouldn't have won a Nobel Prize, because it wouldn't have been revolutionary.
No,
So,
exactly.
It was just really the drive of understanding and exploring the universe that drove me. But the Nobel Prize, that's the...
beautiful bonus.
It's a beautiful bonus, that's right.
Exactly. That was a great question. Do we have any more? We're
Yeah,
very close to wrapping up.
yeah, sorry about that, Wodonga. I know that the bridge dropped out there for a moment, so you probably missed a little bit of the middle of that one. But we have to move on. So I'm wondering if Leon Garthra Secondary College in Victoria is online. We haven't spoken to you yet.
Hello.
So, yep.
Hi.
Hi. Have you got a question for Brian?
I was wondering, does the accelerating expansion of the universe mean that for a point X distance away from Earth, Hubble's constant will change over time?
Yep, so that's a very sophisticated question. So the question would be, if you have a point, this is a question one of my graduate students might ask me, so I'm going to do my best to answer. So the answer is yes. If you have a point and you can make a good enough measurement, you can actually see the object's velocity change in time and speed up. Now, there's a new generation of telescopes called the extremely large telescopes, of which the ANU is a partnership through the Australian government in one of them called the Giant Magellan Telescope. And it is just possible we can use these new telescopes to do that experiment. It is really, really hard because you really want to do it over 1 million years rather than 10 years. Then it would be easy. But over 10 years, it's really, really hard. But it is true, those objects, you'll actually see them speed up over time.
Thank you.
Thank you.
What's your opinion on extraterrestrial life forms?
Well, I think I'll know it when I see it, but I haven't seen any yet. I think in my lifetime, we're going to be able to check nearby planets and see if they have the signatures of life in them. But at this point, I presume there's so many chances for it, it will exist in some form, but we have not seen it, and so therefore I do not know. But it is something I think we'll be able to do, again, with these next generation of extremely large telescopes that we're building.
Okay, thanks.
All right, well, thank you so much once again for all of those questions.
Yep.
It is now time for us to end our video conference. I've certainly had a great time and learnt a lot. I just want to take the time now to thank a few of our partners for allowing this to happen. We'd love to extend a warm thank you to our Director of Questacon, Professor Graham Duran. It's always lovely doing these video conferences in such a lovely space. We'd also like to thank the New South Wales Department of Education and Communities. Polycom, thank you once again for all of this beautiful equipment that we're using. The ANU for letting us have you for the moment. And also all the schools, thank you so much for streaming. We do love your involvement. And to our beautiful, lovely, laughing studio audience and various VIPs and prestigious guests that we have, thank you so much for coming along. We've had a great time. You can all give yourselves a big round of applause if you like.
Shine the screen.
And so any schools that are disconnecting now, if you've got some further questions, send them into live@questacon.edu.au. We'll see if we can answer them after the event. Otherwise, we'll say goodbye to everyone at the far end. See you later.
Bye.